Thank you very much for that kind introduction. I'm very happy to be here with you all today and excited to talk about one of my favorite topics, dry hopping. Today I'm going to talk about a lot of work that I worked on or collaborated on when I was a PhD student in Dr. Thomas Schellhammer's laboratory at Oregon State University. But before we jump into some research, I think it's important to understand why dry hopping has become such an important issue. Over the past couple of years, the craft brewing industry has had a profound influence on the beer industry in the US. Currently, at 8,764 breweries, the US has the most breweries opened at any time point in its history. Although there was a reduction in 2020 because of COVID, we see here that craft beer production has grown significantly in the US since 2007. In 2020, craft accounted for 12.3% of the overall beer production volume and about 22% of the overall market share, with a market value of over $22 billion. Here we see the growth in production of IPAs, or India Pale Ales, over that same time period. And these are beer styles with very hop-forward flavor profiles. In 2020, IPA made up almost 40% of craft production and about 4% of the entire US production, with an estimated market value of $8.5 billion. It's not surprising to see that more hops are needed to make these hop-forward beers. Here is the average hopping rate in gram per hectoliter reported by craft brewers in the US, and we can see that over this time it's also increased. Just to put this into context, the average hopping rate in 2018 was about 10 times that of what's in American Light Lager, or Bud Light, which these beers still make up a lion's share of the US production and market share. The growth in hop usage has not surprisingly had a profound impact on the hop industry in the US, and the type of hop varieties being produced has completely shifted from 70% alpha, seen in light green, and 30% aroma in 2007 to 73% aroma, 27% alpha in 2020. The main hopping methods that are used by brewers are kettle hopping, late hopping, and dry hopping. If we look at the average hopping rates used to make commercial American lager and IPAs, it's apparent that significantly more hop material is being added to IPAs as compared to American lagers. This is because brewers are adding significantly more hops during dry hopping. In the next few slides, I'll indicate why that's the case. So historically, hops were mostly added to the kettle during the boiling of wort, and hop aroma in kettle hop beers is low because a lot of the hop aroma is lost during the boiling of wort. And the main flavor contribution of hops is to add bitterness to beer. Hops contain alpha acids, which are not bitter or soluble. However, when subjected to heat, alpha acids isomerize into isoalpha acids, and this reaction is one of the main flavor chemistry reactions that describe hop flavor in beer. The conversion to alpha acids to isoalpha acids is dependent on temperature and time. So the longer hops are in contact with boiling wort, the more isoalpha acids are formed and the more bitterness you get. Therefore, as you expose hops to heat for shorter time frames or add hops at lower temperatures, less isoalpha acids are formed. Therefore, brewers have turned to dry hopping as a way to impart unique aromas without imparting bitterness. There are a number of different ways that brewers dry hop, so it's impossible to define exactly how all brewers perform this technique. However, generally speaking, dry hopping is defined as the cold extraction of non-volatile and volatile chemicals from hops into partially or fully fermented beer. As you can see, dry hopping features much cooler extraction conditions than kettle hopping, so no isoalpha acids or bitterness is contributed. However, much longer time periods are used to extract essential oil components out of the hops. And the main driver of hop aroma during dry hopping is imparted by that essential oil, which is made up of a number of different compound classes, as seen on the right. These compound classes are described as spicy woody, such as the monoterpenes, citrusy, fruity, and floral, which the oxygenated compounds, which can be esters or terpene alcohols, and then tropical catty, like the thiols. This brings us to the first manuscript that I'd like to discuss. Although dry hopping has been a technique used by brewers to increase both the microbial and flavor stability of beers since the 1890s, the hopping rates that U.S. brewers are currently using are about 2 to 3 times those historical rates. And at the time I started my research in 2015, there was not much literature to evaluate how efficient these dry hopping rates were at extracting aroma. Therefore, we designed a dry hopping rate study by taking cascade hops from the same 10-pound mini bale and dry hopping them at that hop at 4 distinct levels: 2, 3.8, 8, and 16 grams per liter. We felt that these rates encompass the hopping rates that you would generally see in the industry at that time frame. Briefly, here's a schematic of our dry hopping process, and further details of this method are outlined in the manuscript by Vollmer et al. In the Journal of American Society of Brewing Chemists. Just briefly, we performed the dry hopping event in duplicate with 40 liters of unhopped base beer that was commercially produced. We then dry hop that beer at the target rate for 24 hours at 15.4 degrees C. After that time frame, we then blend those two treatments together, filter through a cellulose pad, and then what we're doing post-filtration is measuring dissolved oxygen to make sure that we were at or well below 110 parts per billion. After this specification was met, we then collected the beer, carbonated it, and then had it ready for sensory and chemical analysis. Essentially, what we were doing here is taking that unhopped base beer and making a hoppy beer tea out of it. Now, for all the studies that I'm going to talk about today, we performed quantitative descriptive analysis to evaluate the sensory profiles of those beers. In general, our panels were made up of 7 to 13 panelists. We used 3 to 4 days to train the panel on the hoppy characteristics and the samples that they would be evaluating. And then each rating that you'll see is an average of 4 to 6 replications per individual. So each individual rated that beer 4 to 6 times. We then use analysis of variance for data analysis and as a tool to ensure that the sample effect that we're seeing is real and that there's no interactions for panelist or replication. And then we use commercial and pilot beers as references to hone our panel on the given attributes that we want them to evaluate. And I just want to point out that they're only smelling these samples. And so here's the attributes that they looked at. And I'll talk about overall hop aroma intensity in this slide. So let's dive into some results. So here's the overall hop aroma intensity on the y-axis and dry hop rate on the x-axis. Now what I mean by overall hop aroma intensity is the intensity of the beer above the unhopped base beer. And you can see the unhopped base beer here is the E sample, or the sample where E is above. So that sample had aroma, but hopping increased the aroma intensity, and that's what we wanted the panelists to scale, is that intensity increase. What should jump out is that the relationship between hopping rate and overall hop aroma intensity is not linear and seems to plateau as we reach the higher dry hopping rates. Therefore, we're seeing diminishing returns as we get up towards those higher rates. Now, if we consider the hop aroma quality, here are the results for herbal tea in green and citrus in orange. We can see that the panelists could discriminate between the samples using these aroma qualities for both herbal and citrus. However, the response for herbal was also very similar to overall hop aroma intensity. They sort of had the same trend. However, if we consider citrus, we see that the herbal quality seems to be suppressing the citrus quality score at these higher rates, the 8 gram per liter or the 16 gram per liter. There are 2 takeaways here. As you increase dry hopping rate above 8 grams per liter, you seem to be getting diminishing returns from your hops when static dry hopping. The other thing is that the dry hopping rate, as you increase the rate, is modifying the aroma quality that you're getting extracted from the hops. We also wanted to confirm these sensory results using some chemistry. So based on the concentration of some terpene alcohols, linalool, geraniol, and nerol, measured in the beer and in the hops, we observed that as the dry hop rate increased, the calculated percent terpene alcohol extraction amount out of the hops decreased. And you can see the top graph there, that only 25% of the linalool concentration in the oil was extracted from the beer at a 2 gram per liter rate. When considering this data along with the sensory data, we feel that this is evidence that simply increasing the dry hopping rate is not a very efficient way to extract aroma from hops. It also indicates that there may be some brewing value left in these spent hops after dry hopping. Now, at the high dry hopping rates, we also observed other changes that were occurring in the beer chemistry. The following manuscript, published in the Journal of Agricultural and Food Chemistry by Christina Hahn, highlighted the importance of humulinones along with isoalpha acids in driving beer bitterness in hop-forward beers. Humulinones are naturally occurring in the hops, as they are the oxidation product of oxidation product of alpha acids. Interestingly, in the current study, we see that over the different dry hopping rates, humulinones were found to be about 78% extracted on average. What you see here is that as the dry hop rate increases, the concentration of humulinones is also linearly increasing. Therefore, although bitterness was not considered in the study, it's hypothesized that as you increase dry hopping rates, bitterness quality and intensity might change in hop-forward beer styles that you're dry hopping. As a quick aside, we recently investigated the sensorial characteristics and consumer preference of North American consumers towards 42 different non-alcoholic beers. Under the assumption that humulinones are only resulting from hops and being extracted into beer via dry hopping, we used the relationship between dry hopping rate and humulinone content to estimate the dry hopping rates for the NABs in this study. About 48% of the NABs contained humulinones. And what we found here in the bottom graph is, here you see the overall aroma liking for the consumer and train panel, is that the NABs with an estimated dry hopping rate of about 600 to 800 gram per hectoliter were the most preferred by the consumer panel, while the NABs with estimated rates above 800 gram per hectoliter had more herbal tea characteristics and had less and were less liked from an aroma perspective. So to summarize, simply adding more hops might not be the best way to add more hop aroma. Further, dry hopping is also having an impact on other parameters in the beer matrix, such as the extraction of humulinones on beer, and this might modify the beer bitterness. These other impacts should be considered and accounted for in the design of dry hopped beers. Therefore, we thought that exploring other simple techniques that promote hop aroma extraction might be beneficial. One technique that jumped out right away, because a number of brewers were already using this technique as a marketing tool, was double or triple dry hopping, or essentially splitting a high dry hop rate into multiple smaller additions. Therefore, we designed another dry hop rate study by taking centennial hops from the same mini bale and performing single and multi-stage dry hop events. The single stage treatments were done at 3.8, 8, and 16 grams per liter, like the last study, and the two-stage dry hop events were performed by doing consecutive dry hopping additions that added to the cumulative rate of the single stage dry hop treatments. For example, we did two 1.9 gram per liter treatments for the 3.8 gram per liter, two 4 gram per liter treatments for the 8 gram per liter treatment, and two consecutive dry hop events for the 8 gram per liter dry hop consecutive events for the 16 gram per liter. These samples were produced in a very similar way to the last study, except we extended the dry hopping time to 96 hours to more mimic the commercial brewing practice. And for the two-stage events, the first edition was added for 48 hours, and then we moved the beer into a second set of kegs for the second edition, and then we filtered the beer after 48 hours to stop the dry hopping event. For the single stage, we left that beer in the same keg for 96 hours. So here are the results for overall hop aroma intensity for the different treatments as a function of the dry hopping rate again. The results for the base beer are on the far right. Again, that's the E sample in gray. In the single stage treatments are here in red, and the open circles are the two-stage treatments. We can see that compared to the single stage treatments at the same rate, the multi-stage dry hopping resulted in significantly more aroma being extracted. For example, if we look at the 800 or the 1600 and the 800 gram per liter treatment, we can see that both of those treatments, that multi-stage was significantly higher than the single edition in terms of aroma intensity. What is interesting, though, is as we observed in the previous study, there seems to be some diminishing returns past 800 grams per hectoliter, because the two-stage 800 gram per liter treatment had the same aroma intensity as the two-stage 1600 gram per liter treatment. This shows that splitting a larger dry hop charge into two separate doses leads to more effective aroma extraction and ultimately better hop utilization. From a bitterness perspective, although these effects are really rate dependent, the two-stage treatments resulted in slightly higher bitterness units and higher humulinone concentrations, as well as a decrease in isoalpha acids. It's not clear how this would impact the perceived bitterness, intensity, and quality, because humulinones have been shown to be about 66% as bitter as isoalpha acids, but it's something that you should be keeping in mind as you design hop-forward beers or dry hopped beers. We then worked with a regional craft brewery in California that's world-renowned for its IPA production to perform this experiment on the commercial scale as well. And for the single edition, they dry hopped 350 hectoliters of their flagship commercial IPA at 733 gram per hectoliter for 12 to 14 days at 20 C. While for the two-stage edition, the beer was dry hopped initially at 366.5 gram per hectoliter, and then after 3 to 5 days, a second edition of 366.5 gram per hectoliter was then added to the beer. After the beer production was complete, the beers were then cold crashed and then filled into kegs until sensory and chemical analysis could be performed. It's important to point out, too, that we replicated both the single edition as well as the two-stage edition. So here's a principal component analysis, or PCA, that can help us visualize the sensorial differences among the different treatments. The circles in blue represent the different sensory characteristics that we measured, and we can see along the first axis that it's really defined by overall hop aroma intensity, or OHI, meaning that as you moved from left to right in the plot, the samples are increasing in aroma intensity. And then we can see within each rep again, the single stage is in red and the multi-stage is in open. As you move from left to right, within the rep, you're increasing in aroma intensity. So just as an example, this was the single stage and this is the multi-stage. And the multi-stage at the commercial scale also had more aroma intensity. It's also interesting to point out that rep 1 was lower in aroma intensity. And this is important because this sample these reps were brewed about a month prior to rep 2, indicating that there's a decrease in aroma intensity over the shelf life in terms of the hoppy beer intensity. However, what we can see is that the multi-stage dry hopped beer is performing better from a flavor stability standpoint, and that it's maintaining some of its hop aroma intensity. So it's clear that the two-stage or multi-stage dry hopping yields beer with significantly more aroma, but it's not clear how this procedure might modify bitterness quality and intensity. Similar to the first study, there seems to be diminishing returns above 800 gram per hectoliter. Therefore, if you're looking to dry hop your beer with a significant amount of hops, you might consider performing multi-stage dry hopping if your cellar has the space and capacity. Finally, I would like to discuss the benefits of blend hopping and harnessing the unique biochemical of hop varieties to make dry hop beers with unique and novel flavors. So a bit of background before we dive in. Before we started on this experiment, Dr. DeCoy from Sapporo Breweries published this really interesting study in Brewing Science. He showed that blending hops with different aroma chemistries could promote synergistic effects and impact the aroma quality of dry hop beer. To highlight this, they evaluated the aroma characteristics of solutions that had single and multiple volatiles spiked into them. For example, if they took the thiol formin P and added it to a mixture of linalool, geraniol, and beta-citronellol, this new mixture had a really intense tropical note that the other individual component mixtures didn't have. This paper also highlighted that blend hopping could be used to increase and modify the aroma extracted from hops during dry hopping. Therefore, because of this, we decided to explore blend hopping a bit. To do this, we used a fourth degree simplex lattice design and made 15 different dry hop beers with blends of Cascade, Chinook, and Centennial. These blends are shown graphically here by the ternary plot. We then used descriptive analysis to evaluate the aroma qualities and intensities of these beers. For those unfamiliar with reading the ternary plot, the point here at the top represents a beer dry hopped with 100% Chinook. As we move down the plot, we reduce the amount of Chinook in the blend and increase the amount of Centennial along the left side or Cascade along the right side. So the blend on the left here would be a 75% Chinook, 25% Centennial blend, while the blend on the right would be 75% Chinook, 25% Cascade. As we move to the next row, these would be blends made with 50% Chinook. Again, this next row would only contain 25% Chinook. And then finally at the bottom, these blends contain no Chinook and are just binary mixtures of Centennial and Cascade. Here are the sensory results. I know this is a really busy table, but I just want to highlight two things. The sensory results are sorted by increasing overall hop aroma intensity, and by using Fisher mean comparisons in ANOVA, we can see that there are significant differences in the aroma intensities and qualities for these different blended treatments. Now, it's hard to see trends in that table, so we perform hierarchical cluster analysis on the descriptive analysis results, and three main clusters were formed. As one would expect, the 100% Cascade, 100% Centennial, and 100% Chinook were in the three different groupings, and each defined a group. So you can see the red was defined by Cascade, the green was defined by Centennial, and the blue was defined by Chinook. This suggests that dry hopping with each of these varieties leads to beers with varietal-specific hop aroma intensities and qualities. It's useful to point out, too, that breweries have successful beer brands marketed off the unique aroma profiles of these varieties. For example, Sierra Nevada Pale Ale is made solely with Cascade, while Bell's Two-Hearted Ale is made exclusively with Centennial. However, these results also point to the fact and highlight that hop blends might also be able to be used to emulate the unique profiles of single hop ales. If we overlay these wort clusters now onto the ternary plot, we can see which blends provide us with similar aroma profiles to the 100% treatments. Although there are some minor discrepancies, these regions offer a starting place to help brewers select blends of these three popular aroma hops, which lead to similar aroma profiles during dry hopping. Again, another way we can look at the sensory data is to use principal component analysis. And again, the first axis, or the left to right axis, is really defined by overall hop aroma intensity. So that PC1 or F1. Now we can add in our treatments, and I just want to point out where the single cultivar treatments are. You can see on the far left, there's 100% Chinook treatment in blue. And then as we move from left to right, we're increasing intensity. So the next most intense sample, single hop ale, would be the 100% Cascade. And then the most intense sample would be the 100% Centennial and Green. If we then overlay the cluster analysis onto the PCA, we can see that using the binary or tertiary blends of the 3 hops increase the hop aroma intensities for the blended treatments above the single hopped beer. So just for example, if we look at the 100% Chinook treatment, it's in the bottom left of that grouping. And so as you would blend in Cascade or Chinook, you would move the sample toward the right, and you're increasing hop aroma intensity as well as modifying the aroma quality of that sample. So I think it's not surprising that our observations showed that hop varieties have varietal-specific dry hop aroma profiles. However, what we think is really interesting is that blending hops during dry hopping seemed to promote an increase of dry hop aroma intensity, and that certain blends were found to lead to similar aroma profiles and intensities to the single varietal treatments. Overall, we feel these results show that dry hopping with blends could be a useful tool for brewers. We feel that brewers could use these studies to help determine which blends might actually help them create target dry hop aroma profiles and create more flexible and sustainable brewing recipes, because it would allow for substitution if a certain variety had a shortage, or if you had an oversupply for another variety. Now, one thing I didn't cover was that dry hopping can lead to considerable beer loss. Therefore, investigating process approaches to recover or minimize beer loss, such as centrifuge or hop cannon, could be useful. Also, reducing the amount of vegetative matter you're adding to the beer by utilizing alternative hop products could also be an essential consideration. So finally, I would like to recognize and thank the Alexander von Humboldt Foundation for their support. Without the support, I would not have had the opportunity to share this work with you all today. And I also want to point out that most of this work has been previously published. So if you found any of the articles particularly interesting, just reach out to me, and I'll shoot you the manuscript. And with that, I would love to take any questions that you might have.